Good morning, good afternoon, or good evening, depending upon where you are in the world, and welcome to today's webinar, 800-volt AI server power supply topology challenges, brought to you by EE Times, Allegro Microsystems, Aero Electronics, and broadcast by AspenCore. I'm Colleen Heckman, and I'll be your moderator today. I have just a few brief announcements before we begin. First, the slides will advance automatically throughout the event. You may also download a copy of the slides by clicking on today's slide deck in your resource folder located to the right of the presentation window. Today's presentation will be followed by a lively Q&A session. So please ask questions at any time during this webinar. Just type your question into the Q&A text area and hit the submit button. If you experience any technical problems during the webinar, you can type an issue into that same Q&A text area, hit the submit button. We'll be glad to offer you one-on-one assistance. And now, on to the presentation, 800-volt AI server power supply topology challenges. Discussing today's topic are Anna Chiu, Strategic Marketing Manager for High Voltage Power at Allegro Microsystems. Anna holds a Master of Electrical Engineering, Electronics Electrical Engineering degree from National Taiwan University of Science and Technology and 10 years of industry experience. She currently serves in strategic marketing at Allegro and the isolated gate driver product line, where she's responsible for the AI power market. And joining Anna today is Thu Vu, Principal Systems Engineer for High Voltage Gate Driver at Allegro Microsystems. Thu holds a PhD in Electronics Engineering at Maynooth University and a master's degree in Electronics and Communications Engineering at Dublin City University. Thu was the lead design and innovator of the high-efficiency multi-level PFC and LLC technologies for iSurgy Limited. He currently serves as a lead product definer with a focus on architecture HV isolated gate drivers at Allegro. It's with great pleasure. I'm going to now turn things over to Anna to begin. Anna, take it away.
Okay, thank you. Thank you, Colleen. Hello, everyone, and thank you for joining today's webinar. My name is Anna Chiu. I'm a strategy marketing manager for the isolated gate driver product line at Allegro Microsystems. Today, we will talk about a very important topic in AI power design. What are the challenges of 800-volt AI server power supply? How the move toward 800-volt AI server power architecture is changing PSU topology, and why isolated gate driver design is becoming more critical. As AI computing power continues to increase, power density and efficiency become major challenges for the whole power infrastructure. Allegro has been invested in this area, and our goal is help customers simplify power design, reduce design risk, and improve system-level performance. And now, let's take a quick look at today's agenda. First, I will give a brief overview of the AI data center power trend and why the industrial is moving toward the higher voltage power architecture. Second, we will look at the PSU topology challenges, especially what changes when PSU power moves toward 30 kilowatts and 800 volt. Third, Thu will explain why gate driver and isolated bias design matter and why common mode noise become a system level problem. Finally, we will introduce Allegro power through technology and show it can simplify the design and reduce common mode capacitance. Okay. Before we go into PSU design, I want to first highlight one important architecture change in AI server power. In traditional server power architecture, power conversion is more closely integrated inside a server rack, and it is low voltage system. Nowadays, AI chip power consumption keeps increasing. The traditional approach's 48 volt system reach its physical limit. The high current brings more copper, large cable, and more space pressure inside the rack. Thermal management efficiency also become problems. So in the new 800 architecture, we started to see that IT rack and the power rack being separated, like the photo we show on the slide. The IT rack mainly focus on computing like CPU and GPU. Between IT rack and power rack, there is a 800-volt DC link here. And this creates a new protection point before the voltage, a high voltage DC enter the IT rack for rapid protection. We called it is SSCB, solid state circuit breaker. In the power rack, we call it the SIRAC, handles power conversion. Its output support 800-volt DC power distribution. With higher voltage, we can make the power architecture easier to scale. So let's see how this shapes PSU design. The key trend is clear. As AI computing power continues to increase, rack power also keep moving higher. The HVDC migration also changed the PSU design. At 800 volt, the PSU needs to handle higher voltage stress, higher isolation requirements, and more complexity topology. We also see the PSU power rating moving from lower power level to around like 30 kilowatts and beyond with the three-phase input. So 800 volt is not only a bus voltage changes, it's a full power architecture migration. And this is migration create a new design challenge inside the PSU. Now that we see the big shift to 800 volts, let's talk about what that means in practice. The next challenge is how the power stage itself evolves. When PSU power moves from around to 30 kilowatts, the biggest changes is not only the power rating. The real change is the topology. In the low power design, we often see similar PFC architecture, but for 30 kilowatts high density PSU design, the industry is moving to a more advanced topology, such as like this one, T-type PFC, Vienna PFC, or flying cap C, or other multi-level structure. On the DC-DC side, LC still remain the very important topology. These topologies helps improve efficiency and power density, but they also create a new challenge. They require more floating switches, more isolated gate drivers, and more isolated bias power rails. Every floating switches needs a reliable gate driver and a clean isolated bias supply. Once the number of switching increase, the number of isolation power domain also increase. So let's use T-type PFC as an example. It requires multiple isolated domain, maybe 7 or even more. We face cascade design challenge. Usually it is interleaf topology. All the components need to be doubled. So the isolated transformer is also required. And it's not only the size issue, it also creates characteristics capacitance across the isolation barrier. So this capacitance becomes one of the major source of the common mode noise. So the topology change is not only power stage challenge, it's direct impact gate driver design, bias supply design, EMI, and system reliability. So let's see. With so many components we see in previous slide, it brings engineer the physical design so difficult. In high density power shelf, the available space is very limited. The power rack size is usually standardized, and the height is constrained by 1U, like this one, 1U form factor. In the example, the driver board height is only around 30 millimeters, but inside this limit space, you need to fit in all the components, like 12 lots of components in this limited the small car. So this creates few major challenges. The first challenge is layout. When the board become crowded, it is hard to keep the gate loop and power loop compact. This can lead to like ringing, voltage overshoot, and switching noise. And the second challenge is isolation. Usually multi-level topologies such as T-type or Vienna PFC require more floating power domains. That means more isolated bias rails and more isolated barriers. So for 30 kilowatts PSU design, the challenge is not only choosing the right silicon carbide FET. The other need to think about is how to build the whole gate driver and bias power architecture in a compact, reliable, and EMI-friendly way. Why we keep mentioning bias power design and transformer? Besides the physical design challenge, the second major issue is the common mode noise. Common mode noise is strongly related to common mode capacitance. In isolated gate driver and isolated bias supply, one major source of common mode capacitance is the transformer or the isolation barriers. When the switching knot move very fast, like very high DVDT, can push current through this capacitance. This current become like common mode current. And the common mode current can create several system level problems. First, like EMI become harder to pass. Engineer, you may need larger filter, extra chokes, or additional time to fix it. Second, voltage spike can disturb your system and make your system upset. In serial case, this may cause like reset, malfunction, or components damage. And the third one, the common noise also can couple back into signal chain or control loop, creating false signal or control error. Finally, rapid charging or discharge the capacitance also wastes power and can reduce system efficiency. So low common mode capacitance is not just a gate driver spec, it becomes a system level design requirement. In short, the shift to 30 kilowatts PSU means more advanced topology, more isolated domains, and common mode noise at system level headache. Now, Chiu will take us deeper into how the noise is generated in details and how we articulate the isolated solution to keep it in check. Chiu?
Thanks, Anna. So in order to appreciate the issue highlighted by Anna in the previous slide, we will look into a conventional gate drive solution for 30 kilowatts AI PSU. And from the system level view, the gate drive solution needs around 36 isolated and non-isolated bias supply rail and has around 54 isolation barriers need to be managed. And this is the level of the complication that we need to deal with here. Now, if you look at the example here is the schematic of the PSU with three-phase 480 volts AC input. And the BFC used a T-type neutral point clamp topology to rectify the AC input and boost the voltage up to around 800 volts. And the T-type NBC topology is similar to the Vienna rectifier, except that the 1200 volts silicon carbide diodes are replaced by the 1200 volts active switches for conduction loss reduction. And as a result, the T-type NBC gonna need 6 isolated gate driver for the boost switches, and in addition to the 3 isolated gate driver for bidirectional back-to-back switches. And as you know, for conventional isolated gate driver would need the power supply on the high voltage side. So gate driver with different reference on the high voltage side will need separate isolated bias supply, while gate driver with a common high voltage reference, for example, here in this case here for the low side, can share the same bias supply. And based on this principle, so we gonna need around 7 isolated bias supply rail in total for the T-type NBC PFC, right? And now after the PFC stage, what we have here is the boost voltage of VBOC here need to go through an isolation DC-DC converter before connected to 800 volts bus. And the isolation stage in this example is a 3 interleaf PLC converter, which is commonly used for the high voltage application due to high efficiency, compact transformer design, and reduced output cone ripples, which are very important, and also low EMI noise. So you can see here for the LLC resonant capacitor on the primary side can be connected either in delta or Y configuration, and the delta connection is actually more beneficial as it's going to require lower capacitance value. And now if we look at the gate driver, the LLC stage gonna need 18 isolated gate driver for both primary side and then secondary side switches. And we assume here that the LLC MCU is actually placed on the secondary side, actually on the output of the LLC, right? And since the LLC is operating at 50% duty ratio, the LLC low side gate driver can be shared an isolated bias supply, while the high side gate driver here, the high side gate driver, can be powered by non-isolated supplies. For example, in this case here, we can just use bootstrap diodes plus a resistor here, right? And bootstrap diode supply, of course, is very simple and very easy to implement. However, the solution is limited to certain application that needs to allow the initialization during startup. That's the first thing. And also the application that have no extreme duty ratio, and also application that don't need negative supply, just like, for example, a PFC. So the LLC stage require, like, in general, you can see here only 2 isolated bias rail and 9 non-isolated bias rails. And you may notice in the schematic here that we only running just one phase, handling around 15 kilowatts. So then for the complete system, we need to double up the number of gate driver, the number of bias supply, and the number of isolation barrier. And since common mode capacitance and EMI noise mostly coming from the bias supply, so we're gonna dig deeper and then going into how the 9 bias supply rail for the PFC and then LLC are generated in the next slide. Right, so a common approach to isolated bias supply design here is to start with a flyback converter, which normally exists in the system for housekeeping. So the input to the flyback converter could be either from the PFC stage or could be the rectified AC input. And the flyback converter will have multiple outputs, and one of them in general going to be used just for the voltage regulation, while the other output here, here, and here normally relied on cross-regulation, which means the flyback outputs are not fixed and tend to change depending on the loading condition. So the bias supply for the LLC primary side and secondary side can be generated by adding the windings to the existing flyback transformer. And its flyback transformer output will be rectified and then regulated by an LDO to achieve 18 volts supply. Bias for the BFC low side, 3 BFC low side, can be generated in a very similar way, except that we are using the 21 volts here, LDO. And also we use a zener here to generate a negative supply of 3 volts. And you may notice that the PFC stage gonna need like have negative supply, while the LLC stage don't need negative supply. This is because of the fact that for the reliable turn off, so we're gonna need the reliable turn off during hard switching, we're gonna need the negative supply. Now, since PFC high side device and back-to-back switches, they have like their source floating and swinging from one potential to the other. So care must be taken when designing the bias supply rail, because on the isolation transformer, you can see here, actually gonna introduce the common mode noise into the switch, into the system. And that's when gonna cause the problem during the PFC operation. An example for the PFC high side negative high side supply design here is we're gonna get 12 volts from the flyback converter, and then we are using either open loop LLC or open loop push-pull to generate the bias supply rail 1, 2, and 3. And each rail here can have separate transformer for common mode capacitance reduction, and the output of the open loop LLC in general need to be regulated because it's going to be load dependent. And again, here we gonna use 21 volts LDO and plus a zener to generate the negative supply. So the bias supply for rail 5, 6, and 7 can be generated in a very similar way, right? So for the next slide, what we're gonna do is we're gonna look at different bias supply topologies and we will compare them. Right. Now, there existing a lot of topologies, for bias supply and also control method. But here we will focus on something simple and low power solution and commonly used in data center application. The first solution shown in the left-hand side here is an LLC operating in open loop at a fixed frequency, and the frequency can be between 500 kilohertz to 1 megahertz. And due to high switching frequency and no limitation on the leakage inductance, the LLC transformer can make very compact and also with very low common mode capacitance by separating between the primary side and secondary side windings. And thanks to soft switching and low common mode capacitance, the LLC offer low EMI noise with very low common mode current. The common mode capacitance for the LLC in general will be between 3 to 5 picofarad, right? Now, with the open loop LLC, you can see here, because the voltage to the LLC will be from the 12 volt flyback, so we still have the variation at the input voltage. The LLC in general can have fixed gain if we are operating at resonant frequency. That result in the variation at the output voltage of LLC depending on the load, and also you also have the variation at the input here. As a result, we're gonna need the LDO at the output of the LLC just to regulate the voltage, right? And because of the LDO, and also we're gonna need the transformer driver and other components, so LLC solution has high component counts and also high cost, right? So similar to the LLC, we have another one is an open loop push-pull, which is also very commonly used in AI power supply design. So the push-pull design can operating also very high frequency, similar to the LLC design. However, the design for the push-pull transformer here is quite complex because we're gonna need the center tap input and also center tap output. And the inductance between primary winding and secondary winding of the push-pull transformer also need to be minimized, and this result in higher common mode capacitance. We're talking between 7 to 10 picofarad in this case, which means we're gonna end up with higher common mode noise. And regarding the output voltage regulation, you can see that it's something similar, which means the LLC, the push-pull here also need an LDO to regulate the output voltage. And also we also have another issue with high component counts and costs. And the third approach is to add another winding to existing flyback converter. This approach is simple, lowered component counts. However, since flyback converter is operating at high frequency, at low frequency, between around like 100 kilohertz to 150 kilohertz, the transformer gonna be quite bulky with a lot of common mode capacitance. We're talking about much greater than 15 picofarad. So flyback is less preferable from EMI noise and common mode capacitance point of view. And another thing that I want to highlight here is if you look at all the three options here to generate the bias supply, and all of them also couldn't generate, like negative supply, we're gonna need additional circuit in order to generate the negative supply. And now let's look at a few options here if we want to generate a negative supply, right? And the negative supply, as I mentioned before, we need that just for hard switching, because for the SiC device, if we want to turn it up reliably, we tend, like the recommendation is to use the negative supply. And of course, if you have active Miller clamp in the gate driver, that also helps just to achieve very clean turn off. Right. There are a few common approaches to negative rail generation. So the first approach is on the left-hand side. And what we can use here is just use either a Zener or the shunt regulator to split the output voltage from single output, which is 21 volts, to dual output here, which is minus 3 volts and 18 volts, with reference to 0 volts here, right? And the negative supply will be set by the Zener or the shunt regulator. The shunt regulator, of course, can allow very accurate regulation and fine tune, but it's gonna cost more, while the Zener option will just give you a discrete step in terms of selecting the negative supply, but it's the cheapest solution. And another thing here is, let's say that we have the unbalanced condition between loading condition between turn on and turn off. So normally the power will dissipate in the Zener or the shunt regulator, right? Now, the second approach here is to add an output windings to the isolation transformer. For example, in this case, we have the flyback converter. And the output winding gonna generate the negative supply, while the extra winding is actually generate the negative supply, and the main winding is generate the positive supply. And the turn ratio is used to adjust in terms of, the negative and the positive. And because of that reason, so then we need quite a lot of good control to select or fine tune the negative supply. And this option also have higher costs because you have to add more windings to the existing transformer and making everything a lot bulkier. And the third option here is just to use a buck-boost converter. And with the buck-boost converter, as you can see here, it's actually can achieve very good efficiency, but it has a lot of components and it's very expensive. So it is normally it's not practical for the AI power supply application. So far, the conclusion is it's actually generating negative supply is not free, and it's only add cost and complexity to the bias supply design. Now, in this slide, we will go back and we'll analyze how the common mode current flow in the NBC PFC stage and how that impact the system design. So isolated bias supply account for more than 90% of the total common mode capacitance, as you already see that. So because the capacitance in the isolated gate driver will be much less than 1 picofarad. Normal design, if you can see, you can see that they're going to be between 10 to 30 picofarad common mode capacitance in one gate driver and one bias supply. And it may not sound a lot, but it can generate a significant upsurge and common mode current in the control and drive circuitry. And this depends also on the VDT, right? So now we have a look at the switch node A here, right, of the NPC lag. So the existing common mode capacitance in between the switch node A and ground, and that is due to the isolated supply number 3 here, connected like that will supply the power to the isolated gate driver driving the high side SiC device, right? And assume that like this, if this isolated supply here, supply number 3 has around 30 picofarad, then when the high side switch here, let's say when it turn on, immediately they're gonna be swing going from 400 volts to 800 volts. And this swing here, if we assume that around 100 volts per nanosecond, so even with just around 30 picofarad, you're gonna see around 3 amp of common mode current flowing from this switch node here, right? It's because it's going, the node going high, which the capacitor gonna get charged. So that's why the current gonna flow on the whole way back to the MCU here, right? And then going through the share ground plane, and then return through the bone cap. That is the line here, the dashed line here is the line where the common mode current gonna flow, right? So now the common mode current, when it's flowing through the share ground plane, it's gonna cause the ground bouncing. So it's causing quite a lot of issue regarding the ground bouncing. You're gonna see that it's gonna impact or pollute the PWM signal. And in a lot of scenario, when the ground bouncing is so far, you're gonna get a very unreliable and faulty operation, right? And the second thing here is when this capacitor gets charged and discharged, for low frequency, it may not cause a lot of switching loss due to charging and discharging the capacitor. But when you have high switching frequency, then charging and discharging capacitor can result in additional loss. And of course, depending on how you design the mechanical and thermal heatsink, so this additional capacitance can introduce back some of the noise going back to the system, and that result in a higher common mode noise. Right now, what we did here is just to verify the theory that we discussed, and the setup we have here is we perform some tests with the half bridge using different bias supply with different common mode capacitance value, and measure the common mode current. And the switch node here gonna go between 0 to 400 volts. So what we test here for 3 commercial solutions. The first commercial solution has around a 34 picofarad capacitance. And when we measure the return of the common mode current, what we got here is around like 2.2 amps peak current. The second solution has around 150 picofarad common mode capacitance. And when we measure and when we found out that is actually in the second solution here, they're using a common mode filter. As a result, the level of common mode current, peak current, is much lower. But then what you end up is a lot of more ringings. And sometimes ringing in a long period of time, it will causing even worse, and it's harder to filter out. And for commercial number 3, where there is only around 2.2 picofarad capacitance, you can see there is a much lower amount of common mode current, and it's much nicer and cleaner waveform. Okay, here I want to touch another topic is the issue of having multiple isolated bias rail with different isolation requirements. And now let's revisit the bias supply architecture diagrams. So as you can see, bias supply 1, 2, and 3 are for the high side device, which is floating between 0 and 800 volts. And as a result, the isolation between 1, 2, and 3 would be 800 volts. And also the isolation between bias 1, 2, 3 and ground will be 800 volts. Now, for the bidirectional switch, and then the bidirectional switch, the source for those switch is basically swinging between 0 to 400 volts or 400 volts to 800 volts. And therefore, the isolation between them will be around 400 volts, right? And also isolation between them with ground will be around 400 volts. But then if you look at the isolation between V bias 3 and V bias 5, it will be around 800 volts. So the whole complication here is when you have multiple isolated bias domain, you have to understand what are the isolation requirements, and then correspondingly in the PCB design, you have to space them out, and then you have to manage them to make sure that all the isolation requirement will be met. And that will complicate the whole PCB design, and also taking more space. As Anna mentioned before, we need more space because we need to fit more components in a very compact area. But now if you have to manage a lot of isolated bias domain, and require space to separate between them, then you don't have much space left in order to fit components. An example I want to show here is just a PCB layout where we show that they're going to be between, let's say, for 800 volts between 2 bias supply here when we design for the high-side switches, right? So as you can see there, for high-side switches, you still have 800 volts isolation between them, and then you have 800 volt isolation between the high side and then the low voltage side. And as if you're counting the number of the isolation barrier here, so you need to cross the isolation barrier for the bias supply, but also for the gate driver. And in total, you're going to need around 5 isolation barrier. And in this case here, we're just talking about, right, just 2 bias rail, right, supplied to 2 isolated gate driver. When you imagine you have around like 18 of them, and you have to get them on running around in a very small board space area, that is where the complication gonna get you. So I hand it next to Anna. Thanks, Anna.
Okay, thank you, Trey. From Trey's explanation, we can see the common mode capacitance is one of the key source of common mode noise. In an 800 volt PSU system, the VDT is already high. We cannot get rid of it because fast switching is also part of how we achieve high efficiency and high power density. So the key design requests become how we can reduce the capacitance across the isolation barrier. This is exactly where Allegro power through isolated gate driver can help. Power through, you can see left-hand side, that is the typical isolation gate driver solution. It requires two power transfer. One is power transfer, another is signal transfer. And the right-hand side is Allegro power through solution. That is we integrate isolated gate driver and isolated bias power into one integrated solution with ultra low common mode capacitance. In next slide. On the left-hand side, you can see the traditional approach. The layout is more complicated, and the design needs to reserve space for the isolated bias supply transformer and multiple isolation boundaries. And remember, this is just only one channel. And right-hand side is Allegro's power through gate driver solution, and it provides much cleaner and more compact implementation. The designer also has more freedom to optimize the gate loop and the power loop layout. Now imagine applying this to a T-type PFC or Vienna PFC design, where there are many floating switches. The benefit will become much more significant. It is not only about saving PCB area, it is also about reducing design complexity, lower EMI risk, and helping engineers get to market faster. Here we compare common mode capacitance across different solutions. Allegro power through solution, that one is the green one, this one. And it shows very low common mode capacitance. It can be more than 10 times lower than many traditional approaches. So the test data Trey just shows is not only a lab result. For high voltage power conversion design, we can reduce the VDT since we like to get higher efficiency and power density. But from the equation, you can realize reduce and manage the common mode capacitance can help reduce common mode current a lot. Okay, so here I'd like to introduce Allegro power through technology. The idea is simple. In traditional gate driver design, customer need a separate isolated bias supply, like here is a transformer and DC-DC controller. You can see the picture below here. You can see the benefit. The gate driver circuit can be more than 50% smaller. In our product portfolio, we have EMOGAN gate driver and silicon carbide gate driver. For EMOGAN gate driver, AHV-A5003 and AHV-A5043 are chipsets. Sorry. So here for the A5003 and A5043, this silicon carbide are the chipset solution for silicon carbide gate driver, and it's provide integrated bias supply, negative turn-off voltage, and active Miller clamp function. And this one is the module solution. That is A5311. It comes with the same function as the silicon carbide chipset solution. So and this one, A5110 and A5111 is the EMOGAN gate driver, which provide the transformer integrated, and also for the A5111, it's also integrate negative power. So key message is simple. Power through helps customer remove the external bias supply, reduce PCB space, lower common mode noise, and simplify system design. Now I'd like to use solid-state breaker as another example. As we talked very beginning, in the new AI power architecture, the 800-volt DC link between the power rack and IT rack needs fast and reliable protection. But SSCB design is not easy. First, the system needs to support 800-volt VDC, so the isolation requirement becomes higher. Second, thermal management is critical. The breaker needs larger power devices and enough heatsink area. Third, the available PCB space is limited. So the designer needs to fit the gate driver, bias supply, protection circuit, and sensing circuit, everything into a very compact space. This creates the same challenge we just discussed earlier: more isolation, more bias power, more layout complexity. With this, in this two block diagram, we can see how power through helps simplify the solid state breaker design. The left-hand side, this one, is the traditional approach. It requires more components and more isolation boundary, but with Allegro power through technology, this helps reduce the external bias, simplify the isolation boundary, and make the layout more compact. For solid-state breaker application, A5311 and A504303 silicon carbide gate driver are great fit solution. It helps improve design simplicity and support faster development. So here, this table summarizes Allegro power through product portfolio. We have solution for both EMOGAN and silicon carbide application. You can find all audible part number here in the table. And here I want to emphasize for chipset solution, this one, A5000, A5040, and this one, A5003 and A5043. We have application note available on website to provide you the transformer recommendation and the spec if you want to build your own transformer. All evaluation boards for whole product family are also available, except the AHV A5311, which is currently sampling. The other products are already in production. If you need samples or evaluation board, please contact Arrow or our distributor partner, Arrow. Please contact us or our distributor partner, Arrow. Okay, then I'll hand this back to Colleen.
Excellent. Thank you. Thank you, Tua and Anna, for an awesome presentation. To our audience, we are now moving on to the question and answer portion of the event. So if you haven't done so already, you can go ahead and enter your question in. We do have quite a few questions to get through, so we're going to do our best. If we don't get to your individual question, someone will follow up with you after the program is over. So I'm going to go ahead and get started here. So the first question asks, for applications involving silicon carbide or GaN devices, the dV/dt value under the worst case condition can reach greater than 100 volts ns or even to 200 VNS. What level of CMTI is required for isolated gate drivers to withstand the worst case scenario? And Tua, you are on mute, sir, if you are answering.
Yes, I can take the question. Thank you very much for the question. So in general, in the way we are testing our gate driver internally, we will test the CMTI at both high voltage and also high CMTI. And then the level when we select it will be below the level that we can pass the CMTI. And also another thing here is when you looking at the CMTI for your application, for example, right? When you're talking about greater than 100 volts per nanosecond or 200 volts per nanosecond, so you can see here that the gate driver itself is only introduce a small amount of common mode capacitance. But then if you have the bias supply, that introduces a lot of common mode capacitance. That amount of common mode capacitance basically causing a lot more triples. Not only, like just the gate driver can pass, let's say, 100 to 200 volts per nanosecond, but then that common mode capacitance from the bias supply can create a significant amount of common mode current and causing the ringing that's going to pollute the PWM signal going into the input of the gate driver, and that will lead to faulty operation. So my recommendation here is, yes, select the gate driver with high common mode capacity, select the gate driver with very high CMTI value, but also you need to pay attention to the bias supply design. Otherwise, you may see that the problem is actually the gating problem is not the gate driver itself, but is the power supply design. Thanks.
Thank you. Thank you very much, sir. Okay, quickly moving along here. Again, we've got several to get through. The next question asks, on slide number 8, I'm not following the 2 phases. You have a 3-phase input and everything looks like 3-phase output. There is another set of components, another phase that's not shown, perhaps?
I can take this question also.
Yeah.
Yes, it's probably I didn't clarify enough regarding on slide number 8 here. So what I meant 2-phase here is that we have, let's say we have the PFC stage, it's NPC, and this one here, let's say that if we have to handle 30 kilowatts, in general, there will be another NPC in parallel with this one here. So what example I show in the diagram here is only for one, let's say you can call it one phase, handle 15 kilowatts, and then you need another thing in parallel in order to be able to handle 30 kilowatts. And the same also for the LLC stage.
Excellent. Well, thank you very much. Okay, moving on here quickly to our next question. The open loop LLC seems to be more advantages compared to, or seem to have more advantages compared to other topologies. Is there any downside of having high leakage and inductance in the LLC?
Yes, I think I can answer that one there. So basically, the LLC can handle or can have high leakage inductance, but then you will see that with high leakage inductance, normally what you end up here is the first thing is gonna limit the operating frequency or the resonant frequency of the converter. So when you have low operating frequency, then you also need to design the transformer correspondingly. That's the first thing. And the second thing here is, let's say that if you try to operate above resonant frequency because the leakage inductance is so high, you have low resonant frequency up there, you have to bring it up to much higher in order to reduce the size for the transformer. What you may end up here is the voltage drop across the leakage inductance. And therefore, you're going to have a lot of variation at the output voltage of the LLC.
Excellent. Thank you, Thu. Next question asks, is it possible to use the bootstrap supply for the PFC high side gate driver?
No. So it's its own way possible, but then you have to remember that there's certain restriction regarding the limit, like the extreme duty ratio. And also you have to remember that in some scenario, like the use of the bootstrap supply is actually it's not working. Let's say that if you need a negative supply, so in that case, there you cannot bootstrap a negative supply. So it works in general, but as I mentioned in the presentation, if you can afford to have the initialization during the startup, if you don't have the extreme duty ratio, and if you don't need the negative supply, then it's highly likely you can use a bootstrap for high side supply.
Excellent. Thank you, Thu. Next question. What's the main advantage of Allegro's power through technology compared with a conventional isolated gate driver plus external bias supply solution?
I can answer these questions.
Thank you.
For this one, the main advantage, I would say, it is integration. Power through integrate the isolated gate driver and the isolated bias power into one solution. In a conventional design, customer usually need to separate isolated DC-DC supply, transformer, negative rail circuit, and lots of components. That will add the PCB area, bone cost, isolation complexity, and the most important is common mode capacitance. So with power through, the bias supply is generated through the gate driver solution. It is generated through the gate driver solution. So customer can reduce external components, simplify layout, and lower common mode noise. So I will summarize this with like 3 keywords: simpler and smaller and lower noise.
Excellent. Nice summary. We've got actually another follow-up about power through. Is power through technology suitable for both PFC and LLC?
Yes, I think power through can be suitable for both PFC and LLC, especially for PFC like T-type Vienna flying cap. This multi-level topology, there are many floating, so power through is the best fit for this kind of application topology, I'll say that. But for LLC, usually customer use the bootstrap, but like Trace just mentioned, bootstrap also has multiple like bottleneck. So for the LLC, power through still fit in this topology.
Excellent. Okay. Looks like we're going to be able to fit in maybe a couple more, certainly this next one. This question asks, hi, I'm working on an 800 volt SSCB, and for that need to use isolated housekeeping PSU for gate driver and controller as well. So could you please suggest a suitable PSU and gate driver?
So
or MCU, housekeeping PSU.
I think I can take this question.
Sure.
So we definitely can recommend the gate driver. Regarding the PSUs, we are not designing the PSU, so but we can work with you in terms of your requirements, and please contact us via Arrow. Then we can suggest you the suitable gate driver, and also in terms of your application, what would be the need. We basically can recommend.
Okay, well, thank you both. That does look like all the time we do have for questions today. For more information related to today's webinar, I do suggest you look at any of those resource links. There are several available in your resource folder, as well as requesting a sample in your widget on your audience console. Within the next 24 hours, you will also receive a detailed follow-up email with information on how to access today's program on demand. So thank you for attending today's webinar, 800-volt AI server power supply topology challenges, brought to you by EE Times, Allegro Microsystems, and Arrow Electronics. This webinar is copyright 2026 by Aspen Core. The presentation materials are owned by or copyright by Allegro Microsystems, and the individual speakers are solely responsible for their content and opinion. So on behalf of our guests, Allegro Microsystems and Arrow Electronics, I'm Colleen Heckman. Thank you for your time, and we hope you have a great day.
Thank you.